Deep in the Large Magellanic Cloud burns a star so hot it defies what science once thought possible. HD 269882 pushes the very limits of temperature, light and stellar physics. How can something like this even exist? If you enjoy uncovering the universe's extremes, please like, subscribe and share, and tell us in the comments, what do you think could survive near a star this powerful? Thank you for watching. Now let's begin. The Large Magellanic Cloud rests near the Milky Way as a modest companion galaxy, with its own slow rhythms of gas, dust and starlight, and this wide setting forms the outermost environment for any single luminous object within it. On these scales, the interstellar medium spreads in layers that differ in temperature and density, with cold neutral clouds drifting as islands inside a warmer diffuse sea, and here and there hot cavities left behind by earlier generations of massive stars. Neutral hydrogen traces long filaments that curve across the galaxy, while fainter molecular pockets hide where dust is thick enough to shade fragile molecules from harsh ultraviolet light. The overall mix of elements heavier than helium is lower than the Milky Way average, and that single fact shapes many outward signs of the environment. Dust is somewhat scarcer radiation travels farther before it is absorbed, and winds from bright stars can clear channels through low-density gas with fewer obstacles. The galaxy shows a loose bar bright star-forming complexes and faint tidal features drawn out by long interaction with the Milky Way and with the small Magellanic Cloud, and those interactions seed gentle shocks that can nudge gas into ridges where gravity takes hold. Pressure varies across this landscape, with turbulence layering the medium into patches of denser clumps and thinner lanes, and magnetic fields thread the gas in smooth arcs that help guide charged particles and align dust grains, leaving a polarizing imprint on starlight that crosses the width of a cloud. Cosmic rays add a quiet background of ionization, altering chemistry in shielded interiors and keeping parts of the medium slightly warm even when no bright star sits nearby. Where young associations of massive stars cluster together, their combined light pushes outward and ionizes large volumes of hydrogen, and the edges of those zones glow as sharp boundaries between hot interior gas and the surrounding neutral medium. Superbubbles created by earlier clusters linger for a long time, their shells marking where sound waves once ran, and where the memory of past energy input still holds the gas at slightly lower density than its surroundings. Inside such cavities, the mean free path for a photon is longer, and radiation couples more to free electrons than to dust grains, a subtle change that increases the reach of light and lessens the chance that it will be trapped near its source. The ambient ultraviolet field across the galaxy is stronger than in a heavier element environment, because it is absorbed less readily by dust, so even far from any single association, the sky has a mild, pervasive brightness that keeps thin layers of gas ionized at very low levels. In the denser clouds that do survive, dust provides shielding that allows molecules to form, yet the balance still reflects the leaner chemistry of this galaxy. Carbon monoxide can be faint relative to hydrogen, and observers who rely on that single tracer must adjust their estimates to recover the true mass. Cold clouds cool through line emission and can collapse into denser cores if they reach the right combination of pressure shielding and gravity, but shear flows across the galaxy can also stretch them into filaments that resist collapse until they encounter a shock or collect enough mass along their length. The kinematics of gas show ordered rotation around the bar mixed with local flows that run along filaments, and at the junctions where streams meet, slow shocks compress sheets of material that later fragment into clumps. Each of these clumps sits inside a wider pressure field set by surrounding shells and by diffuse radiation, and that field changes on longer timescales than the lifetime of a single bright star, so a newborn massive object inherits a context that was prepared by earlier neighbours and distant events. Dust grains fewer in number than in a richer environment still play an outsized role in mediating the journey of light and heat. Very small particles soak up ultraviolet photons and re-radiate in the infrared. Larger grains scatter optical light and soften sharp shadows, and both classes together shape how far radiation can travel before it is absorbed. Because grain abundance is lower, the balance tilts toward more transparent lines of sight, so remote clusters and nebulae can be seen through thinner veils than would be typical in the Milky Way. That transparency does not mean emptiness. Rather, it means the same mass is distributed with fewer opaque anchors, and photons scatter more on electrons than on dust, especially inside wide ionized cavities. Maps across wavelengths present a layered picture of this outer environment. Radio images reveal broad pools of neutral hydrogen in and around the bar. Infrared maps trace dust warmed by nearby stars and highlight lanes that cut through luminous regions as cool streaks. Optical and ultraviolet views outline edges where ionization fronts advance into neutral gas, and sketch drifts of scattered light where dust remains. Together, these views show a medium built from nested structures tens of parsecs across for shells and superbubbles, down to much smaller cloud cores where densities rise by factors of many over the surrounding diffused gas. The pressure inside those cores balances gravity only for a time. Elsewhere, the diffuse field sets. The sound speed fixes how fast a disturbance can cross a region and sets the rate at which thermal energy leaks away. Magnetic fields measured indirectly through polarization and line-splitting thread this entire scene and resist compression along one direction, while allowing material to slide along the field, so filaments often align with field lines across wide areas. Through this web flows a gentle background of starlight from older populations spread across the galaxy. Those older stars provide a baseline illumination and a mild heating rate, and on top of that baseline sit the dramatic contributions of young associations that ionize and sweep. The result is an interstellar setting with stronger contrast between thin clear channels and denser clumps, a greater reach for ultraviolet photons, and a tendency for hot low-density cavities to persist and overlap. In such a place, any single luminous star will find that its light travels farther, its radiation pressure couples efficiently to free electrons, and its wind meets an ambient medium already shaped by previous activity. The environment is not static. Shells drift and fade, filaments shear and cloud, edges evaporate under ultraviolet light. Yet these changes occur on timescales, long enough that the broad conditions remain steady as a frame for local phenomena. This outer frame matters for every later layer nearer to a bright object, because it sets the boundary pressures, supplies the material that can be ionized or swept into rims, and controls how far photons and wind particles can go before they slow. It also sets the background against which observers interpret brightness and colour, since a lower dust content alters how much reddening a line of sight accumulates, and thus how intrinsic spectra should be recovered. In this galaxy, the difference in metallicity and dust has many small practical consequences for observation and for physical behaviour. Alike, ionized fronts stand out more sharply, diffuse halos around bright sources extend farther, and the thermal balance in thin gas leans toward higher temperatures because cooling lines are fewer and dust cooling is less efficient. The outer environment, with its mixture of transparency, filamentary structure and enduring cavities, forms a gentle but decisive stage on which luminous stars imprint their presence, and from which their influence expands. In this broad context, the galaxy's gas and dust provide the light, the lanes, and the pressure that define what the farthest edges of any stellar domain look like before one approaches the nearer regions where wind radiation and gravity begin to carry a single signature. Within the broader galaxy, the star's immediate neighbourhood narrows to a swath of interstellar space where young massive stars often gather in loose associations, and where their combined output sets the tone for gas, dust and light on scales of a few tens of parsecs. A stellar association is a gravitationally unbound or marginally bound community that shares a common origin. Its members drift together through the same corridor of space with similar motions, and their youth is marked by blue colours, strong ultraviolet emission, and the presence of ionized hydrogen regions. In such a neighbourhood, the medium is not uniform but carved by overlapping bubbles, shells and channels, traced by the winds and radiation of multiple bright sources. Ionization fronts ripple outward from the strongest members and sometimes meet, forming bright rims where densities rise and cooling lines glow. The collective radiation field of the association lifts electrons off atoms across wide volumes. So low-level ionization persists even in nominally diffuse zones, while denser clumps hold their neutrality until starlight erodes their edges. Dust grains drift through this entire scene, and being fewer than in a higher metallicity environment, allow more ultraviolet photons to pass between members. As a result, the association feels more interconnected through radiation than a similar group in a dustier galaxy would. The balance between stars and gas is dynamic. Winds sweep material out of the central lanes, piling it into arcs that curve away from the brightest sources, and where two winds meet, thin shock layers wrinkle into filaments that then cool and fragment into knots. These knots can host secondary smaller generations of star formation if pressure and shielding align, but even when they do not, they mark the pattern of past flows and survive as sculpted structures that guide later motion. The density of stars across the association is not even. Some subgroups cluster more tightly, while others spread out, and this unevenness sets a patchwork of influence where certain directions show sharper ionized edges or deeper cavities. Kinematics observed in emission lines reveal mild velocity gradients that track the drift of the group through the galaxy, and show broadening from turbulence driven by winds and radiation pressure. In the outskirts of the association, the radiation field softens and shells grow thinner, merging into the wider galactic medium, yet the imprint of the group can still be traced by faint arcs and by polarization patterns that indicate aligned dust grains along the flow. The star's neighbourhood also includes a background of older, lower mass stars that contribute little to the ultraviolet field but add to the gravitational potential and provide a low level of optical light that sets a baseline illumination. Their presence helps stabilize the large-scale environment without erasing the youthful signature of hot blue members. On the scale of a few parsecs around any single bright star, the combined association field establishes the boundary pressure that a stellar wind must push against to open or maintain a cavity. If the ambient pressure is moderate and the gas is thin, an individual wind can carve a nearly spherical bubble that expands until it reaches pressure balance. If the ambient medium is denser or structured by previous flows, the bubble elongates along the easiest path and can vent into pre-existing channels, making lobes and faint chimneys where hot gas escapes. The radiation from nearby massive stars adds to that of any given member, so ionization fronts pushed by one source can be sustained by the photons of neighbours when geometry allows line-of-sight access. This leads to nested or overlapping regions where the exact contribution of each star varies with angle, and it also leads to subtle effects in line ratios, because the spectrum that reaches a patch of gas is a blend filtered through dust and gas, along several paths. The association exhibits a hierarchy of ages spread over a few million years, a typical pattern in which dense cores form and disperse in waves, leaving behind subgroups with slightly different ages and slightly different compositions. Younger subgroups often sit nearer dense molecular remnants. Older subgroups lie in cleaner cavities with sharper shells. The star under consideration inhabits one of these layered zones, and the precise arrangement of shells, filaments, and ionized edges around it reflects the sum of recent history: who formed first, who cleared which lanes, and how the wider galactic flows have sheared or compressed the gas. Because heavy elements are fewer here, winds from the group are somewhat different in character line driving. Remains efficient but depends on a sparser set of metal lines, so terminal speeds and mass loss rates balance in a way suited to the environment, and the entire association's energy budget couples to the gas with details that observations can measure in Doppler broadened profiles and in the brightness of specific ionization states. Where the association's radiation strikes a surviving molecular filament, a bright ionization front advances into neutral gas, leaving a thin photoevaporative flow that bends away from the stars. The curvature and thickness of this flow reveal local pressure and the strength of the incident light. Globules at the tips of pillars often point back toward the core of the association, their tails trailing downwind. Inside, the temperature falls and molecules survive, while at the surface, atoms cycle between ionized and neutral states under the steady pulse of ultraviolet photons. Embedded within the group, small clusters of lower mass stars form a quiet backdrop. They add infrared light from warm dust in their disks and modest winds that have little reach compared to the giants, but they seed the field with weak magnetic outflows and contribute to the overall momentum budget in small, widespread ways. The radiation field also sets the surface chemistry of dust grains in the neighborhood. Ultraviolet photons desorb molecules, heat small grains to brief high temperatures, and change the charge state of larger grains, which in turn alters how they interact with gas and with starlight. Over time, overlapping shells break in places where density drops, allowing warm gas to stream into adjacent cavities. Along those openings, turbulence mixes layers of different temperatures and densities, creating thin zones where cooling is rapid and where specific emission lines spike. The association's edges are marked by a gradual shift from ionized to neutral gas, with partial layers that shine in optical recombination lines and in infrared fine structure lines. Their surface brightness falls with distance, and the transition is smoother than in dustier settings because stray ultraviolet photons leak farther. Proper motions of the brightest members show that the group as a whole drifts through the galaxy on a path that intersects older shells and leaves new marks behind, and as it moves, the relative geometry of stars and gas evolves, slowly changing shadowed regions into illuminated ones, and altering which filaments receive the most intense radiation. The neighborhood thereby acts as both stage and instrument. It records the past through shell and filament structure, and it shapes the present by fixing the pressures, photon fields, and flow channels that each star encounters. In this framework, the star sits as one participant among several peers, its light part of a chorus that sculpts the local medium and maintains the ionized glow that outlines the association against the wider galaxy. The result is a coherent but intricate setting, in which distances of a few parsecs matter angles to neighbors matter, and the inherited architecture of shells and filaments matters, and all of these together define the neighborhood before one steps closer to the individual domain carved by a single stellar wind. The space between the association and the single luminous source is filled with diffuse dust and a steady radiation field that together set the color temperature and visibility of everything in view. And this layer defines how light travels long before it meets any denser structure. Dust in this galaxy has fewer heavy elements to draw from, so the overall grain abundance is lower than in the Milky Way, and that change echoes through every optical effect. A dust grain is a tiny solid particle of carbon silicates or related compounds. It scatters and absorbs starlight and then re-radiates the energy in the infrared. The distribution of grain sizes favours small particles, yet with fewer metals, the tail of very small grains and aromatic molecules is somewhat reduced, so ultraviolet absorption is less efficient, and the ambient radiation field penetrates farther. Scattering changes the direction of light without converting it to heat, while absorption turns light into thermal energy inside the grain. The balance of these processes is the albedo. In this environment, the albedo in the optical range sits high enough that scattered light fills cavities with a gentle glow, and the preferred scattering directions lean forward, meaning light tends to continue in roughly the same direction after a deflection. The far ultraviolet field around the star arises from the combined output of the association and from the star itself, and because dust is thinner, these photons cross longer distances before they are absorbed. As they traverse the medium, they photoionize trace atoms, liberating electrons and creating a mild, widespread ionization that cools slowly through faint emission lines. Dust grains also eject electrons when struck by ultraviolet photons, a process called the photoelectric effect. Those electrons heat the surrounding gas, and in a lower dust environment, each grain carries more of the load, so the heating per grain rises even if the total heating per volume is moderated by the scarcity of grains. The gas temperature in diffuse zones thus sits higher than it would in a richer dust setting, and that elevated baseline temperature influences sound speed pressure balance, and the thickness of ionized layers at boundaries. Thermal emission from grains appears in the infrared as a broad band of light that records the radiation intensity they feel. Small grains heat up in brief spikes and cool quickly, while larger grains approach steady temperatures. In maps, these bands trace pale halos around ultraviolet sources, painting a picture of exposure rather than density. And in this galaxy, the halos extend farther, because the ultraviolet field is less easily quenched. The extinction curve describes how strongly dust dims light at each wavelength. Here it rises more gently into the far ultraviolet than in more metal-rich systems, and it lacks some of the features that strong carbon chemistry would provide. As a result, blue and ultraviolet light from bright stars loses less intensity per unit distance, and observers must correct their measurements with care because standard recipes derived from denser dust environments can overestimate the true dimming. Polarization arises when elongated grains align with magnetic fields and scatter or absorb light, more in one orientation than another, and across these diffuse zones, polarization maps sketch the hidden structure of the field that threads the gas. In the surroundings of a very bright source, the radiation field itself can help align grains by spinning them into preferred orientations, strengthening polarization along certain arcs that trace the shape of illumination. The cumulative field of photons and the dust that processes them create a feedback on visibility. In channels cleared by earlier winds, the radiation field runs almost unimpeded, adding a soft floor of illumination, and any remaining grains in those channels scatter enough light to brighten the background. Against that background, shell, rims and filaments stand out with higher contrast, because they present a longer line of sight through dust and gas. Their brightness is a function of geometry, grain properties, and the angle between the source, the feature, and the observer. In areas where dust density rises, radiation slows and warms the grains to higher steady temperatures, and the infrared emission grows. In areas where dust thins, ultraviolet light reaches deeper and maintains a lightly ionized warm phase that smooths gradients and resists compression. The ionization parameter, defined simply as a measure of photon supply per particle, stays relatively high around luminous sources in this galaxy because absorption is lower, and that parameter controls the thickness of partially ionized skins on cloud surfaces. Those skins have temperatures of several thousand degrees, Kelvin pressures set by the local photon density and gas density, and they act like blankets that regulate evaporation into the diffuse medium. The radiation pressure exerted by the field pushes gently on grains, and because grains and gas are coupled by collisions and by electric charge, the push spreads to the gas itself. In dense zones, the coupling is strong, and gas moves with grains. In thinner zones, the link weakens and grains can drift, leading to subtle separations of dust and gas that change local extinction without strongly changing gas density. Across the diffuse environment around the star, these small drifts accumulate slowly and help explain why some sightlines appear unusually clear even though gas columns remain. Photodissociation regions sit at the transition between ionized and molecular gas. There, the far ultraviolet field is still strong enough to break molecules but too weak to fully ionize hydrogen, and dust controls how deep the field penetrates. In this galaxy with fewer grains, these layers are broader and more transparent, with emission from fine structure lines that extends over larger widths than in dustier cases. The structure of the radiation field is not uniform even when the dust is thin. Shadows fall behind dense knots and pillars, and light bends around them through scattering, filling the shadow volume with a dim haze rather than leaving a dark void. The level of that haze depends on the scattering phase function, the grain albedo, and the ratio of scattered to direct light along the path. As the star brightens the local field, these balances shift slightly, raising the scattered component and lifting the floor of illumination in nearby cavities. The cumulative effect is a visual that feels more translucent than opaque, with long sightlines and soft gradients rather than abrupt walls. Diffuse dust also shapes time variability in the field. A change in illumination at the source propagates outward at the speed of light, and the dust responds almost immediately in scattered light, while infrared emission reacts with delays set by heating and cooling times of grains. These delays are short for small grains and longer for larger grains, so the diffuse infrared halo can smooth rapid changes into slower variations, a natural filter imposed by the physics of tiny solids in a low metallicity gas. The ambient field bathes wide areas with ultraviolet photons that drive chemistry on grain surfaces, building and breaking simple molecules and adjusting the charge states of grains. Charge in turn alters how grains stick together in slow collisions and affects how strongly they couple to magnetic fields. Over long periods, this microphysics shapes the grain size distribution, feeding back on scattering, absorption, and infrared emission. In the surroundings of a luminous source in this galaxy, the result is a diffuse medium in which light travels. Farther scattered halos are broader polarization, more clearly traces magnetic geometry, and photodissociation layers spread wider across cloud surfaces. Every brightness, edge color, gradient, and infrared arc in this layer is a map of dust properties and photon density. And this map sets the optical and thermal stage on which closer structures present themselves as one approaches the regions where radiation pressure and ionization concentrate, and where the diffuse field gives way to sharper boundaries maintained by the immediate glow. Around the luminous source, the first distinctly local structure appears as an ionized bubble, a volume where ultraviolet photons strip electrons from hydrogen and maintain a warm, transparent gas that stretches outward until the photon supply balances recombinations. The bubble's interior holds a nearly uniform temperature of about 10,000 degrees, Kelvin set by the balance between photoelectric heating and line cooling, and within it electrons and protons drift freely, while trace atoms of helium and heavier elements occupy higher ionization states. The density is low enough that collisions are infrequent compared to radiative processes, so the gas cools by emitting specific lines and a gentle continuum, and the whole region shines in faint recombination light that records the flow of photons from the star. Because dust is scarcer here than in a richer environment, the ionized zone reaches farther before starlight is exhausted, giving the bubble a larger radius than it would otherwise have, and sharpening the contrast at its edge. That edge is an ionization front, a thin boundary where neutral gas meets the flood of ultraviolet photons. On the ionized side, temperatures stand high and pressures rise, while on the neutral side, temperatures fall, and molecules may persist if shielding holds. The front moves outward early in the life of the region, then slows as the supply of neutral gas dwindles, and pressure balance is reached, and its final position is not a neat sphere, but a shape moulded by density variations in the surrounding medium. Where the ambient gas is thin, the front advances farther, producing lobes that extend along easy paths. Where the gas is dense, the front stalls and wraps around resistant clumps, leaving pillars and scalloped rims that point back toward the star. Inside the cavity, starlight not only keeps atoms ionized, but also exerts a small outward push on free electrons and dust grains, adding to the gas pressure that helps support the bubble against collapse. At even larger radii, the diffuse radiation field of the association softens the gradient, sustaining a low level of ionization beyond the nominal front and turning the edge into a transition zone, rather than an abrupt wall, especially in directions where dust is minimal. The bubble's interior does not rest in pure hydrostatic calm. It is stirred by the outflow from the star itself, a fast, tenuous wind that begins at the surface and accelerates outward under the pressure of light. Far from the star, where this wind has reached its terminal speed of several thousand kilometers per second, it expands nearly freely until it collides with the pressure of the surrounding ionized gas. That collision produces a termination shock that slows the wind abruptly and heats it to very high temperatures, creating a hot, thin layer just inside a contact surface that separates shocked wind from the cooler ionized bubble. Beyond the contact surface, a slower, forward shock can press into the ambient medium and sweep it into a thin shell, and between these two shocks lies a stratified structure that holds much of the mechanical imprint of the star. The hot, shocked wind radiates weakly because of its low density, mainly in soft X-rays and faint lines, and in a lower metallicity environment the cooling is even less efficient, so the hot layer can persist and fill more volume than in a metal-rich case. If the shell finds a weakness in the surrounding medium, it can vent, allowing hot gas to slip into pre-existing channels and leaving the bubble elongated along that path. If the medium is more uniform, the shell remains roughly closed, thickening as sweat material accumulates until pressure inside and outside match. The ionized bubble and the wind zone thus couple through pressure and energy flow. The bubble sets the outer boundary that the wind must support, and the wind supplies the energy that keeps the bubble inflated against the ambient gas. The balance between energy-driven and momentum-driven behavior depends on cooling rates in the shocked wind. In this galaxy, with fewer heavy elements, cooling is reduced, and the energy-driven regime can persist, letting the cavity grow larger for a given mass loss rate. The mass loss rate itself depends on metal lines that absorb momentum from the star's radiation. With fewer lines available, the rate falls compared to a similar star in a richer environment. But the high luminosity keeps the wind powerful, and the terminal speed remains large, so the momentum flux still shapes the local medium decisively. Observationally, the bubble's existence appears in a suite of signals. The warm gas gives off hydrogen recombination lines and emission from doubly ionized oxygen that brighten the interior and the rim. The hot, shocked wind adds a faint high-energy glow where column densities permit it to escape, and the swept shell can reflect and re-emit starlight in the infrared as dust within it warms. Polarization vectors often align along the rim where grains are compressed and ordered, tracing the shell's curvature and the direction of past flow. Kinematic signatures in emission lines show a hollow expansion pattern with slight red and blue shifts on opposite sides as the shell moves. The bubble's pressure sets the baseline against which small, denser clumps feel photo-evaporation, the slow flow of gas off their sunlit faces that feeds the interior with fresh ionized material and gradually erodes the clumps. Each evaporating surface becomes a tiny cometary feature pointing away from the star, and the sum of many such flows adds texture to the interior without breaking its thermal uniformity. Near the ionization front, the gas can recombine faster than the photon supply can maintain if density spikes, creating thin transition layers where temperature drops and the gas changes state over short distances. In a lower dust field, the reach of ultraviolet photons lengthens these transitions and softens their gradients. The outer boundary of the bubble also holds a memory of the association beyond, since external radiation and pressure shape the shell from the outside, while the star shapes it from the inside, and at places where two bubbles meet a shared wall, forms that can ripple with instabilities as shear flows slip past one another. Throughout this region, care is needed to distinguish temperatures. The warm ionized bubble sits near 10,000 degrees Kelvin. The hot, shocked wind reaches temperatures many orders higher that belong to thin plasma, and neither of these equals the effective temperature of the star's visible surface. The separation of regimes matters because each layer radiates and moves in its own way, and because comparisons to other hot objects must be grounded in like with like. The ionized cavity and outer wind together define the limit of the star's immediate influence, a boundary drawn not by gravity but by photons, and by the pressure of a fast outflow. Within that boundary, gas remains highly transparent, dust is thinned and heated, and emission lines carry information about density, temperature, and motion. At the boundary itself, the front marks where neutral gas resists, and where geometry decides which directions open and which hold firm. This coupled system stands as the first local signature one encounters on the path inward, the place where the star begins to imprint its identity on the surrounding medium, and where the diffuse galactic field yields to a domain defined by a single, luminous source. Just inside the ionized bubble and just above the visible surface lies the wind acceleration zone, a layer where starlight transfers momentum to gas and turns a near-static atmosphere into a fast outflow that soon reaches thousands of kilometers per second. At the very base of this zone, the gas still moves slowly, held by gravity and by the weight of overlying layers, and thermal motions set only modest speeds. Radiation arrives from below, with an intensity set by the star's large luminosity, and embedded within that light are countless narrow spectral windows where atoms and ions absorb more strongly. Each time a photon is absorbed in one of these lines, it hands over its momentum to the ion, and because the ion collides with surrounding particles, it shares that push with the gas as a whole. The result is a systematic outward force that, close to the surface, competes with gravity, and gradually winds coaxing the gas through a point where the outflow becomes supersonic and then continuing to feed speed into the expanding stream. The process is sensitive to which ions are present and to how they are distributed in velocity, because a moving ion samples the star's spectrum at slightly shifted wavelengths, opening fresh lines to absorb as the gas accelerates. This shifting access to absorption channels lets the radiation field keep pushing even as the gas speeds up, and it is one reason the acceleration can continue across many stellar radii. The density in this zone falls with radius as the flow expands, and that decline changes both the number of absorbing ions per volume and the rate at which collisions couple the push from ions to neutral species. The outflow remains well tied together because charges and collisions occur frequently enough to keep all components moving as one fluid, yet the mixture shows structure on small scales. Tiny variations in density or velocity can grow because places that move a little faster see a slightly different slice of the spectrum and absorb differently, and that difference feeds back into the force they feel. These growing ripples seed, clumping in the wind, creating pockets that are denser than their surroundings, and gaps that are thinner while the overall acceleration continues. In a galaxy with fewer heavy elements, the catalogue of lines available for absorption is sparser, so the total momentum the radiation can extract per unit time is somewhat reduced compared to a richer environment, and the mass carried away per second tends to be smaller. Even so, the high luminosity maintains a strong line force, and the terminal speeds remain very large because speed depends strongly on how efficiently each gram of gas can be pushed, rather than on how many grams are pushed. The acceleration profile through the zone follows a smooth rise from near the surface to well into the outflow, slow at first, while gravity still dominates, then steeper as radiation takes control, and finally easing as the gas approaches its asymptotic speed. The exact shape of that rise depends on the distribution of line strengths on the ionization balance, and on how quickly the velocity increases with radius, because a faster gradient separates absorption features in frequency space and reduces self-shadowing between layers. Ionization itself is set by the intense ultraviolet field of the star and by the density of the gas. Nearer the surface, where density is higher, some ions retain electrons and offer many strong lines, while farther out, where density falls and the radiation remains, hard ions reach higher stages and the forest of useful lines thins. This changing mix shifts where the push is most effective, biasing the acceleration toward regions where the right ions are abundant and where the velocity gradient keeps fresh absorption windows opening. Heating and cooling in the wind acceleration zone differ from the conditions in the wider ionized bubble. Here the gas takes up energy through photoionization and through the mechanical work of acceleration, and it loses energy by line emission and by adiabatic cooling as the flow expands. The temperature settles into a range that keeps hydrogen mostly ionized, but leaves heavier elements spanning several charge states a balance that also feeds back on which lines drive the flow. Magnetic fields thread the zone frozen into the ionized gas and stretched outward by the wind. If rotation is present, the field can wind into a spiral pattern that exerts a gentle sideways tension, but in the absence of strong magnetic confinement, the field follows rather than dictates the acceleration, contributing only small corrections to the overall radial push. The interaction of small clumps with radiation introduces effective porosity. Dense pockets can become locally more opaque in strong lines, shadowing gas behind them and shifting where acceleration is felt most strongly, while the gaps allow photons to stream farther without being absorbed. This patchwork does not halt the outflow. It modulates the distribution of force and produces a flow where the mean properties still follow smooth trends, but local values wander around those trends. Observationally, the acceleration zone writes its signature into spectral lines that show both absorption at blue-shifted velocities and emission formed by scattering in the outflow. The deepest absorption begins at modest speeds close to the surface and extends toward the terminal speed as the line of sight crosses layers farther out, while the emission spans a broad range of velocities and angles. The exact depth and shape of these features reflect the clumping, the ionization balance, and the velocity gradient in this zone, so careful measurements can recover how quickly the gas accelerates and how densely it fills space. The momentum equation that governs the flow has three main contributors in this region: gravity pulling inward gas pressure providing a small outward nudge near the base, and the much larger radiative line force pushing outward. Because gravity weakens with radius, while the line force can remain strong as long as lines stay available, there is a radius where the net force becomes positive and the gas commits to outward motion. And beyond that radius, the acceleration climbs toward its peak, before tapering. The location of the sonic point where the flow first outruns sound waves sits close to where the radiative force overtakes gravity by a narrow margin, and its position depends on details of temperature and opacity. In a lower metallicity setting with slightly fewer lines, the sonic point can shift a little outward, and the density at that point can be lower, setting a lower overall mass loss rate, while leaving the later acceleration steep. The connection between radiation and motion also controls how the outflow responds to short-term variability. If the star's ultraviolet output changes by a small fraction, the radiation field in the zone adjusts on a light travel time, and the gas responds on a flow time, so minor changes in line strength propagate outward as gentle waves in speed and density. The acceleration zone therefore acts as a translator between the steady radiative power of the star and the momentum carried into space by the wind filtering rapid flickers and passing along slower trends. By the outer edge of this zone, the wind has gained most of its final speed, the density has dropped enough that additional acceleration has little leverage, and the flow transitions into the almost ballistic regime that fills the wider cavity. Yet all of the later structure, all of the shell shaping and pressure support in the bubble beyond rests on what happens here, where photons first take hold of the gas, where small clumps appear, and where the balance between gravity and light sets the mass that the star can lift into space each second. In this way, the wind acceleration zone is both a boundary and a factory between atmosphere and outflow, and a factory that turns radiant energy into ordered motion, with characteristics fixed by ionization line, opacity, velocity gradient, and the leaner chemistry of this galaxy. As the outflow leaves the acceleration zone and stretches into the larger cavity, small differences in speed and density sharpen into embedded shocks, and those shocks, together with the expanding geometry, set the conditions under which many ultraviolet and visible spectral lines take shape. The origin of these shocks lies in the way line driving amplifies tiny perturbations. A slightly faster parcel samples the spectrum at slightly different wavelengths and gains a little more push, while a slightly slower parcel lags and receives less, so the faster parcel can overtake the slower one and compress the gas between them. Where this convergence occurs, a thin shock front forms, converting kinetic energy into heat and briefly raising the local temperature far above the surrounding wind. The shock then cools radiatively, and the gas returns to the general flow, leaving a pattern of clumps and rarefied gaps that ride outward together. This embedded shock network fills a broad radial interval, beginning not far above the sonic point, and running through many stellar radii, and its statistical character remains roughly steady as fresh structures are seeded and older ones expand. The clumps are denser by modest factors compared to the mean, while the gaps are thinner and more transparent. The flow as a whole remains supersonic and nearly radial, but the line of sight to the star passes through alternating layers of different opacity and velocity. The temperature inside a fresh shock can reach values where highly ionized species appear that are rare in the cooler, smoother wind, and as the gas cools, it steps through a ladder of ionization, states emitting photons at wavelengths characteristic of those transitions. Because densities are low, the cooling proceeds mainly by line emission, rather than by collisions, and the radiated energy escapes, quickly leaving behind gas that settles into the prevailing ionization balance set by the star's radiation and by the local density. The presence of shocks explains why faint high-energy emission can arise even in a wind driven by radiation, rather than by magnetic reconnection, and it cautions that temperature in this context refers to a transient thin layer inside the flow, and not to the effective temperature of the stellar surface. Line formation in this wind depends on two broad effects: scattering and emission. Resonance lines of abundant ions scatter continuum photons from the star. They remove light from the direct beam at velocities that match the projected speed of the wind along the line of sight, and they re-emit that light in many directions, producing a broad, sometimes asymmetric profile. Emission lines form where the gas is excited by collisions or by recombination after ionization, and then radiates at preferred wavelengths. These lines often sample a wide range of velocities because the emitting gas is spread over many radii. The velocity gradient of the wind plays a quiet but decisive role because layers separated by small distances can be separated in frequency space by the Doppler shift. So a photon interacts most strongly with the local gas whose velocity matches the photon's shifted frequency. In practical terms, each layer imprints its own narrow slice of the profile, and together these slices build the observed line. The blue shifted absorption trough, often seen in strong ultraviolet lines, forms as photons from the stellar continuum encounter gas on the near side that is moving toward the observer. The deepest part of the trough corresponds to the range of radii where the line is most opaque, and the blue edge approaches the terminal speed where the wind has reached its full acceleration. Emission fills both red and blue wings, as scattered and locally produced photons arrive from all directions, weighted by the density and by the solid angle each layer presents to the observer. In a lower metallicity wind, fewer strong lines mean that certain ions carry more of the diagnostic load. Doubly and triply ionized carbon, nitrogen, and oxygen provide prominent resonance features in the far ultraviolet, while singly ionized helium and hydrogen recombination features appear at longer wavelengths where densities and excitation conditions allow. The clumping introduced by shocks raises the local density inside pockets, which increases recombination and can strengthen emission at some wavelengths, even as the mean mass loss rate remains lower than in a richer environment. At the same time, porous structure can lower the effective opacity along some paths, letting photons escape more easily and changing the relative depths of absorption features. These two tendencies, increased local emission and decreased effective absorption, compete in ways that depend on geometry and on the size distribution of clumps. Observationally careful fitting of line profiles with models that include clumping and porosity yields mass loss rates that are more reliable than those derived from smooth wind assumptions, and in this galaxy such fits consistently find lower rates than analogues in more metal-rich systems while retaining very high terminal speeds. The embedded shock pattern adds another layer of subtlety by producing weak shifting substructures in the absorption troughs, sometimes seen as migrating notches that drift blueward as the features move outward and accelerate. These notches trace parcels of enhanced opacity sliding through the line formation region, and their motion over days or weeks reflects the flow time from the inner to the outer wind. The location of the dominant line formation zone depends on the transition. Resonant scattering lines see large optical depths across a broad radial range and are sensitive to the whole column of moving gas on the near side. Recombination lines often weight inner radii more heavily, where densities are higher, though clumping can shift their effective contribution outward. Lines that require higher ionization stages tend to sample regions closer to the star where the radiation field is harder and where shocks are younger and hotter, while lines of lower ionization stages favor larger radii, where the gas has cooled and where the radiation has diluted. Polarization carries information about geometry and clumping as well. Scattering off free electrons in an aspherical distribution can polarize the continuum slightly, and variations in the line profile across the polarized spectrum can reveal whether emission arises preferentially in denser equatorial flows or in more polar streams. In the absence of strong rotational flattening or magnetic channeling, the wind appears nearly spherical on average, but the clumpy pattern introduces small stochastic changes in polarization that average out over long intervals. The microphysics of excitation and de-excitation inside clumps and shocks proceeds under conditions far from thermodynamic equilibrium. Populations of atomic levels respond to the radiation field, to the electron density, and to the temperature, and because collisions are infrequent, radiative rates dominate. This sets up conditions where metastable levels can be overpopulated relative to a simple thermal distribution producing lines that would be weak or absent in a dense gas. The moving medium further alters the radiation field that each parcel sees because photons escape more easily along directions where the velocity gradient is larger, a directional bias that changes which transitions contribute most strongly to cooling and to line profiles. All of these processes occur while the wind continues to expand, so the residence time of a parcel in any given temperature or ionization state is limited. The most luminous lines are those that can be excited and emitted on timescales shorter than the advection time through the zone where the necessary conditions hold. Even in this complexity, broad tendencies stay clear. A powerful fast wind produces deep blue shifted absorption in strong resonance lines. Embedded shocks add soft high-energy emission and small moving features in profiles. Clumping enhances recombination emission and reduces effective opacity along some paths, and lower metallicity shifts the balance toward lower mass loss rates and longer persistence of hot-shocked layers. Together, these tendencies build the suite of ultraviolet and optical lines that observers use to measure speeds, densities, temperatures, and ionization states in the outflow. In this region, the star's identity is written not as a single number, but as a family of profiles whose depths, widths, and asymmetries encode the physics of shocks and clumps in a radiation-driven wind, a record formed in the layers just outside the acceleration zone, where motion and light first combine to make the spectrum of a very hot, luminous O-type star. Approaching the visible surface, the photosphere presents itself as the thin, radiating layer from which most of the star's light escapes, and for a star of this class, that surface holds an effective temperature near 52,500 degrees Kelvin. Effective temperature is a defined quantity. It is the temperature a perfect blackbody would have if it emitted the same total radiant energy per unit area as the actual star. The actual photosphere is not a perfect blackbody. It bears spectral lines and slight departures from equilibrium, yet the total outward flow of energy can be compared to that ideal to set a single characteristic temperature. At such a high value, the bulk of the emergent energy lies in the far ultraviolet, with only a small fraction shifted into the visible band, so the surface appears intensely blue-white when measured with broad filters and almost featureless to the eye compared to cooler stars whose spectra show many deep troughs. Hydrogen in the photosphere is almost entirely ionized, meaning atoms have lost electrons through thermal energy and radiation. Helium is largely singly ionized, and in the hotter pockets associated with the higher surface brightness can be doubly ionized. This ionization state leads to an opacity dominated by scattering off free electrons, a process that redirects photons without absorbing much energy, and that scattering gives the continuum a smooth character upon which discrete lines sit. Because electron scattering is grey across a wide range of wavelengths, the continuum shape hews closely to the smooth curve expected from a hot radiator, and the classic jump in brightness across the hydrogen edge is muted. The spectral lines that do appear arise from helium and from highly ionized metals whose transitions survive in such a hot environment. At this temperature, strong features of singly ionized helium and of doubly ionized helium, along with ionization stages of nitrogen and oxygen, characteristic of very early O-type spectra, provide the most prominent fingerprints. Emission features can ride atop this pattern when the base of the outflow contributes scattered light back into the line of sight. But the bedrock of the spectrum in this region is the photospheric continuum itself formed, where the optical depth falls to near unity and where photons last interact before they travel into space. The brightness across the disk shows limb darkening shaped by electron scattering and by the steep temperature gradient, but the effect differs from cooler stars because scattering lessens the contrast between deep and shallow views. The edge of the disk remains bright relative to the center, in a way that reflects both the opacity law and the strong radiative transport. The surface gravity set by the mass and radius combines with radiation pressure to set the density scale height, and at these temperatures radiation pressure is a significant fraction of the total, thinning the upper layers and helping to maintain the conditions under which electron scattering dominates. Rotation can introduce a pattern of gravity darkening in which the equator experiences slightly lower effective gravity and can be marginally cooler and dimmer than the poles while the poles appear brighter. Any such pattern at this star must be inferred cautiously from line shapes and from subtle photometric trends, because winds and emission can veil pure photospheric signals. Even so, the concept helps explain why surface brightness might vary with latitude in a way consistent with early O-type behavior, without requiring a large asphericity. The lower abundance of heavy elements in the Large Magellanic Cloud reduces the degree of line blanketing a term for how many metal lines absorb and redistribute radiation. With fewer such lines, the ultraviolet flux can escape more easily, boosting the far ultraviolet and modestly altering the color indices compared to a star of similar temperature in a more metal-rich setting. That change also affects the step from the total emitted energy to the energy recorded in visible bands, the bolometric correction, which becomes large and negative in the usual sense for very hot stars. Observationally, this means that the star's visible brightness underrepresents its total output by a wide margin, consistent with a luminosity of several million times the Sun, despite a comparatively modest appearance in the optical relative to that power. The photospheric layers are thin in radius but rich in physics. Energy flows outward by radiation, with photons scattering many times from electron to electron and sampling the temperature gradient as they random walk to the surface. Each scattering preserves energy and direction, only partially, so the emergent light carries information about both the local conditions and the deeper layers it has sampled. The timescale for photons to escape remains short compared to global evolutionary timescales, allowing the photosphere to respond promptly to changes in deeper energy supply. Yet short-term variations are muted by the large photon heat capacity and by the smoothing action of scattering. The shape and depth of helium lines map the temperature and pressure at the line-forming depths. In very early O-type spectra, the lines of singly ionized helium and doubly ionized helium reach a balance that shifts with small changes in temperature, providing a sensitive thermometer that anchors the classification near the hottest end of the normal sequence. Lines of nitrogen and oxygen in high ionization stages add corroborating evidence, and weak emission components or filled-in absorption near certain transitions hint at the interplay between the base of the wind and the photosphere. Against this backdrop, hydrogen Balmer lines appear shallower than in cooler stars because hydrogen is ionized, and because electron scattering fills line cores with redistributed continuum light. The continuum level in the visible carries a memory of the ultraviolet dominance. Every visible photon is one among many ultraviolet photons, and the photospheric energy budget is thus weighted toward wavelengths that observers cannot see directly from the ground due to atmospheric absorption. Space-based instruments reveal that dominance and allow accurate inference of the effective temperature when combined with models that include electron scattering line blanketing at the measured metallicity and the geometry of the atmosphere. The photosphere is also the place where distinctions of terminology matter. Temperatures quoted for this layer describe the radiating surface, not the hot plasma of embedded shocks higher up, and not the deeper internal temperatures that sustain fusion. When comparisons to other hot objects are made, the appropriate match is to other photospheric effective temperatures of non-degenerate stars, recognizing that some Wolf-Rayet stars report higher effective temperatures because their thin atmospheres and strong winds move the photospheric layer inward to regions of greater heating. In that context, this star stands among the hottest measured photospheres, known for normal stars with emission features common to the earliest O-types, but a continuum that remains photospheric in origin. The pressure and density structure at the surface set the starting conditions for the outflow above, but within this section, the focus remains on the last scattering layers where light is imprinted with the information that observers later retrieve. Subtle variability across hours to days can arise from surface structure or from changing contributions of the innermost wind to specific lines. Yet the continuum stays steady within small limits, as expected for a compact photosphere radiating at high, effective temperature. The whole surface thus acts as a bright, smooth emitter, whose color line set and polarization together encode the temperature, gravity, and chemical environment appropriate to a very early O-type star in a lower metallicity galaxy. Standing here at the boundary where radiation leaves the star, one sees a spectrum stripped to its essentials by high temperature and low opacity, a powerful blue-white continuum shaped by electron scattering helium and high ionization metal lines mapping the hottest end of the normal sequence, and only muted remnants of the hydrogen features that dominate cooler photospheres. The spectrum of a very early O-type star with emission features presents a compact set of diagnostics that together define both temperature and ionization, while revealing the hand of a fast radiation-driven wind at the base of the atmosphere. Classification at the hot end relies on the balance between lines of singly ionized helium and doubly ionized helium on the presence and strength of high ionization metal lines, and on the degree to which emission fills or replaces absorption in key transitions. Near an O2 classification, the helium lines sit at an extreme. Doubly ionized helium becomes strong, while singly ionized helium weakens, signaling that the photospheric layers hold temperatures above 50,000 degrees Kelvin, and that electrons in helium atoms are frequently stripped twice. In parallel, nitrogen and oxygen show high ionization stages, with transitions that arise where temperatures and radiation fields are hard enough to produce ions missing multiple electrons. The continuum remains shaped by electron scattering, which gives it a smooth, bright profile in the ultraviolet and a blue-white slope in the visible, while the line set rides on top of this continuum with depths and shapes that vary with temperature, pressure, and wind emission. Emission in an O-type spectrum appears when the base of the outflow scatters continuum light back into the line of sight, or when recombination and collisional excitation in the accelerating gas produce photons at the wavelengths of photospheric lines. In very hot stars, this emission can partially fill absorption troughs or tip them into net emission, especially for transitions that couple strongly to the moving medium above the photosphere. The result is a hybrid appearance in which some helium and metal lines remain in absorption, anchoring the classification to a photospheric temperature, while others show central emission or broad emission wings that betray the presence of a structured fast wind. The combination is not accidental. It reflects a layered atmosphere where the last scattering of continuum photons occurs close to the surface, but significant line formation continues above in gas that already moves at hundreds to thousands of kilometers per second. Because the Large Magellanic Cloud hosts fewer heavy elements than the Milky Way line, blanketing is reduced and ultraviolet flux escapes more readily, so the spectral energy distribution leans even more strongly towards short wavelengths than it would at the same temperature in a richer environment. That tilt strengthens the ionization of helium and metals and helps maintain the balance of helium lines consistent with the earliest O-types, while also making the photospheric continuum appear slightly less depressed by metal line troughs. The lower abundance also changes the wind signature. Fewer lines to drive the outflow reduce the mass loss rate, but the high luminosity and strong radiation pressure maintain large terminal speeds, so emission features linked to kinematics still span broad velocity ranges even when the wind is leaner. This difference matters when interpreting emission strengths, because reduced mass loss lowers recombination emission in some transitions, yet clumping inside the wind raises local densities in pockets and can partially compensate by enhancing emission where clumps reside. The classification remains tied to photospheric conditions, not to these wind details, and it is within the helium balance and the high ionization metal lines that the temperature scale is grounded. Effective temperature refers to the total radiant output per unit area and stands apart from the higher temperatures found in thin shocked wind zones. The spectrum reflects both regimes, but the continuum and the core of the key diagnostic lines emerge from the photosphere, so statements about the star being among the hottest measured photospheres refer to this surface temperature, not to the transient plasma temperatures in shocks. Comparisons to even hotter Wolf-Rayet stars must be made carefully because their winds can be so optically thick that the effective photosphere sits deeper in hotter layers, and the classification relies on different diagnostics. Here the surface remains photospheric in character, and the lines used belong to the normal O-type system extended to its hottest limit. The shapes of the helium lines also tell of gravity and pressure. At these temperatures, hydrogen-Balmer lines are shallow because hydrogen is largely ionized, while helium lines show widths and depths set by Stark, broadening in a gas with many free electrons. The balance between line widths and continuum brightness helps fix surface gravity when combined with models that include electron scattering and reduced line blanketing appropriate to this galaxy, matching synthetic spectra to observations across the ultraviolet, and visible yields an effective temperature close to the cited value, and a luminosity that, when corrected for the large bolometric adjustment, reaches several million times that of the Sun, consistent with the radiation field required to produce the observed ionization. In the far ultraviolet resonance lines of carbon-nitrogen, and oxygen display P Cygni profiles with blue shifted absorption and red shifted emission signposts of the accelerating outflow imprinted on the star's light. The blue edge of the absorption trough approaches the terminal wind speed, while the depth pattern across velocities reveals the distribution of opacity and the presence of clumps and shocks that modulate absorption on small scales. In the near ultraviolet and optical emission, components can rise in helium and in some metal lines, and subtle infilling of photospheric absorption indicates that scattering in the base of the wind contributes photons back into the line of sight. These wind signatures sit alongside photospheric diagnostics without erasing them, and together they show a spectrum that is simultaneously a thermometer of the surface and a seismograph of the outflow. Polarization across lines offers further nuance. Electron scattering in an almost spherical atmosphere yields very low continuum polarization, but smaller symmetries introduced by rotation by wind structure or by localized bright regions can produce minute wavelength-dependent changes. Line depolarization, where polarization dips at wavelengths dominated by emission, hints that some emission arises in regions with different geometry than the photospheric continuum, adding another layer of evidence for a stratified atmosphere with a flowing outer skin. The metallicity setting also affects the visibility of certain lines. With fewer heavy elements, some weak blends clear from the ultraviolet spectrum, revealing cleaner continua against which strong resonance lines stand out, and the ratio of nitrogen to oxygen lines can reflect the degree of internal mixing that brings fusion products to the surface, a process that early O-type stars can show even while still on hydrogen-burning tracks. Measuring these ratios in a lower metallicity galaxy helps separate initial composition from later mixing, providing a clearer read on the star's history within the constraints of the present classification. The final picture from this spectrum is that of a star perched at the hot edge of the normal sequence, its photosphere radiating a powerful ultraviolet continuum set by an effective temperature around 52,500 degrees Kelvin, its helium and high ionization metal lines fixing the classification near O2, and its emission features marking a fast, clumpy wind that overlays the photospheric signature without defining it. Such a spectrum explains why the star is described as among the hottest measured photospheres, and not as the hottest object outright, and why comparisons are drawn within the class of non-degenerate line-blanketed atmospheres, rather than to shock temperatures or to fundamentally different stellar types. In the context of the Large Magellanic Cloud, the same spectrum demonstrates how lower heavy element content sharpens, ultraviolet dominance moderates mass loss, while leaving terminal speeds large, and streamlines the line forest that normally blankets hot continua, allowing the underlying temperature to assert itself in the clean balance of helium lines, and in the strong presence of high ionization species. Rotation shapes the visible surface by redistributing gravity and light, and for a very hot, massive star, the effect emerges as a gentle pattern rather than a dramatic distortion, because radiation pressure, electron scattering, and a powerful wind smooth sharp contrasts. A rotating star becomes slightly oblate. The equator sits farther from the center than the poles, so the effective gravity, which combines true gravity and the outward centrifugal term, is weaker at low latitudes and stronger near the poles. Gravity darkening is the observational imprint of this gradient. Where effective gravity is, higher layers compress more tightly. Temperatures run marginally higher at the radiating surface, and brightness per unit area rises. Where effective gravity is lower, the photosphere cools by a small amount and the local brightness falls. The result is a disk whose poles can appear subtly brighter and hotter than the equator when viewed from a favourable angle, though the overall luminosity stays fixed by the energy supplied from within. At these extreme temperatures, the continuum is dominated by electron scattering, which softens limb darkening and reduces the contrast that gravity darkening would otherwise present, so the pattern manifests as a measured change in line depths and widths, rather than as a stark two-tone disk. Line profiles carry the clearest signature of rotation because moving surface zones Doppler shift their contribution to the spectrum. The sum across the visible hemisphere yields broadened absorption lines whose width increases with projected rotational speed, a quantity set by the true rotation rate and by the viewing angle. In very early O-type spectra, helium lines and high ionization metal lines serve as the main tracers. Their cores and wings respond to both pressure, broadening from abundant electrons, and rotational broadening from surface motion. So careful, modelling separates the two and recovers a plausible projected rotational speed, even when winds fill or veil some depths. The viewing geometry matters, but without direct imaging one cannot fix it. Instead, spectra constrain the range of allowed combinations of rotation and inclination, consistent with the observed widths and with the minimal polarization seen in the continuum. Polarization gives a second check. In a nearly spherical electron scattering atmosphere, continuum polarization remains very small. But small departures from spherical symmetry introduce a tiny net polarization that depends on the axis ratio and on how light is distributed across latitudes. Measurements that find only minor polarization argue for either slow to moderate rotation or for an orientation where the projected asymmetry is small. These inferences align with line profile analyses that show broadening characteristic of rotation, but not so large as to demand extreme spin in the plane of the sky. Rotation also interacts with the wind just above the surface. The outflow starts where the photosphere ends, and the surface pattern of temperature and flux influences how strongly radiation drives the first steps of acceleration. Slightly brighter poles can feed slightly stronger local line forces, making polar streamlines marginally faster near the base, while a dimmer equator lifts gas with a slightly weaker push. In the absence of strong magnetic confinement, this contrast remains mild because line driving quickly becomes radial, and because scattering smooths angular gradients, yet the pattern can leave small latitudinal differences in the earliest wind, which later observations average out when viewing the integrated hemisphere. The lower metallicity of the Large Magellanic Cloud reduces line blanketing, and thus slightly enhances the ultraviolet flux that sets gravity darkening contrasts, but it also lowers mass loss rates and the density of the near-surface wind, so rotational imprints at the interface remain modest. Surface brightness patterns can include features tied to rotation beyond gravity darkening. Broad low-amplitude variations in photospheric line depths may occur if temperature and density at certain latitudes drift within narrow limits, producing a migrating imbalance across the disk as the star turns. These imbalances remain small compared to the overall continuum strength, and do not impose large color changes because the spectrum is already dominated by a hot blue-white continuum. Any such pattern must be interpreted with care in a star whose wind can add emission near line centers, since changes in the inner wind can mimic or mask true photospheric modulation. The shape of the star influences limb darkening as well. In a purely static absorbing atmosphere, limb darkening follows a simple rule, where intensity falls from center to edge because shallow rays sample cooler layers. Here, electron scattering adds a grey opacity that lets deeper, hotter layers contribute even near the limb, so the disk stays bright to its edge, and the relative brightening of the poles under gravity darkening plays against a limb function that is flatter than in cooler stars. This combination preserves the qualitative picture of brighter poles and a dimmer equator while keeping the absolute contrast low enough that only spectroscopy and subtle photometry can separate it from a uniform disk. Rotation further affects the inferred surface gravity, because the equator experiences a lower effective gravity than the poles. When fitting model atmospheres to spectra, analysts therefore account for the average over the visible hemisphere rather than a single gravity, an average that depends on inclination and rotation rate. The helium line balance used to set effective temperature remains robust against these small gradients because it samples wide areas, and because the temperature differences implied by plausible rotation rates are small compared to the absolute temperature of the photosphere. Nevertheless, the combination of slightly different local temperatures and different electron density across latitude can alter the detailed strength of specific lines by small amounts, providing a path to constrain rotation beyond the broadening alone when data quality is high. Rotation can also mix the outer layers by stirring material along meridional flows that transport angular momentum and trace out slow circulation patterns. At the photosphere, this mixing shows itself not as a surface current one could see, but as subtle chemical signals in the spectrum if processed material from deeper zones reaches the surface. In a lower metallicity environment, those signals help separate birth composition from later transport because initial abundances of nitrogen, carbon and oxygen are lower. Any enhancement detected at the surface can then be tied to internal processes rather than to starting conditions. Such inferences remain cautious because winds remove mass and can expose layers with altered composition as well. Yet within the photospheric context, the links among rotation, gravity, darkening and line strengths inform how much mixing is plausible at the current stage. Magnetic fields, if present at modest levels, may couple to rotation and wind to produce weak azimuthal patterns in the base of the outflow, but without strong confinement the field does not reshape the photospheric brightness map. Instead, the field rides outward with the wind and leaves photospheric diagnostics dominated by rotation and by radiative transfer under electron scattering. The end result is a surface that stays close to spherical, with a mild equator to pole gradient in temperature and brightness, set by effective gravity with spectra, whose line widths and subtle asymmetries reveal projected rotational speed, and with continuum polarization so low that only careful measurements can separate it from zero. In this regime, the star's rotation is neither invisible nor overwhelming. It leaves a measured broadening of helium and high ionization metal lines, a plausible gravity darkening pattern that places slightly brighter poles against a nearly uniform disk, and a small model-dependent correction in the mapping from line depths to surface gravity. All of these factors merge into a coherent picture where the photosphere remains the dominant source of light. The wind only lightly veils selected lines and rotation acts as a gentle sculptor of shape and brightness at the surface without breaking the symmetry that a very hot electron scattering atmosphere would otherwise display. Just beneath the visible surface lies a narrow stack of layers where light and matter stay tightly coupled, and where opacity, the measure of how easily radiation passes, determines how energy rises toward the photosphere. In a star at this temperature, the dominant opacity near the surface comes from scattering on free electrons, which redirects photons without absorbing much energy, and this grey process sets a smooth background through which other forms of opacity add detail. Bound free absorption, in which a photon lifts an electron from a bound state to the continuum, contributes less, here because hydrogen is mostly ionized and helium is largely stripped of 1 or 2 electrons, leaving fewer bound states to absorb. Free absorption, where a free electron interacts with an ion and takes up a photon, adds a gentle broad continuum that grows with density and helps set the depth at which radiation exchanges energy with the gas. Metal lines, even at low abundance, still provide a forest of narrow absorption windows whose combined effect is called line blanketing. In this galaxy, with fewer heavy elements, that blanket is thinner, so ultraviolet photons meet fewer obstacles, and the emergent spectrum shifts some power to shorter wavelengths compared to a richer environment. The total opacity relevant for transport is the Rosseland mean weighted average that emphasizes the least opaque windows through which heat most readily flows. Near the surface, that mean is shaped by electron scattering with corrections from free and the residual bound-free channels, while deeper just below the photosphere, the contribution from many weak metal lines raises the mean enough to steepen the local temperature gradient. Within these sub-photospheric layers, gas and radiation share energy quickly. Collisions are frequent enough that the level populations of atoms and ions stay close to their local thermodynamic values, a condition that justifies treating the material as near equilibrium in the narrow sense needed to relate opacity and emissivity. Photons created deeper in the star have already scattered and been absorbed and re-emitted many times before reaching here, and at each step their energies are redistributed until the spectrum resembles a hot continuum adjusted by the local opacity. The path a photon follows is a random walk with a mean-free path set by the inverse of the local opacity times density. Because electron scattering dominates, the mean-free path is short, compared to the scale on which temperature changes, so radiation samples a roughly uniform environment over each step and drifts outward through many scatterings rather than in a straight line. Hydrostatic balance holds in these layers. The downward pull of gravity is matched by the upward push of gas pressure and radiation pressure. Radiation pressure is large at these temperatures and luminosities because the density is modest and the flux of photons is intense, so the total pressure that supports the weight of overlying layers includes a significant radiative term. This balance sets a small-scale height, the distance over which pressure falls by a fixed fraction, and that length in turn fixes how quickly density drops with radius and how thin the photospheric skin must be. The temperature declines outward, but not precipitously, because radiation carries energy efficiently when electron scattering is strong. The gradient is the smallest value that can still transport the required energy, as set by the diffusion approximation, and if the opacity were to rise sharply at a particular temperature, the gradient would steepen to keep the same energy flux moving through. In very hot stars, an important rise in opacity occurs around a temperature associated with ion group elements, sometimes called the ion opacity bump, where myriad closely spaced lines combine to increase the mean. Even at the lower heavy element abundance of this galaxy, that bump persists though at reduced strength, and it can create a thin zone of enhanced opacity below the photosphere that slightly alters the gradient, and under the right conditions allows a small amount of local convection. Convection is the bulk transport of heat by moving parcels of gas. In these stars it remains weak or absent in the outer layers because radiation is so effective at carrying energy, but shallow convective pockets associated with the ion bump may form where the radiative gradient locally exceeds the adiabatic value. If present, such pockets sit below the visible surface and do not overturn large masses. They stir material gently at a source of microturbulence that can broaden photospheric lines by a small amount, and may seed waves that travel upward into the atmosphere. The reduced metal content softens this behavior by lowering the bump and making the radiative path more dominant, so any convection that appears is correspondingly milder and thinner. The subphotospheric layers also host the transition from deep thermalized radiation to the emergent flux that will escape after only a few more scatterings. The depth where photons last exchange energy with matter is sometimes called the thermalization depth. Below it, absorption and emission keep the radiation field tied to the local temperature, while above it, scattering dominates and photons mainly change direction. In this star, the thermalization depth lies below the point where optical depth equals unity for electron scattering, and the separation between the two surfaces reflects the fact that scattering is efficient, while true absorption is modest. This separation matters because the continuum that observers see is set by the temperature at the thermalization depth, filtered through the scattering layer above, and it explains why the continuum shape can hug a smooth curve, despite the complex microphysics below. Energy packets rising from deeper zones arrive in these layers already in a near steady flow, and the sub-photospheric structure acts as the final regulator that adjusts the gradient so that the outward flux matches the luminosity fixed by the interior. Small changes in opacity due to ionization balance or to the distribution of metal lines translate into small changes in gradient, and the system responds quickly because radiative timescales here are short. That responsiveness stabilizes the surface against rapid swings. A temporary increase in local opacity steepens the gradient, which enhances the transport and restores balance. A temporary decrease flattens the gradient, which slows the transport and again restores the required flux. Acoustic waves and gravity waves launched by stirring in shallow convection or by motion at deeper boundaries can pass through these layers. As they do, their amplitudes adjust to the changing density and pressure, and only a tiny fraction reaches the photosphere with measurable effect. Most dissipate or reflect without leaving lasting marks, consistent with the small amplitude variability typically recorded in the visible output of very hot O-type stars. Magnetic fields, if present at modest strength, remain frozen into the ionized gas and move with it. Just below the surface, their tension and pressure are small compared to gas and radiation, so they neither halt transport nor restructure the gradient, though they can guide the fine structure of any shallow flows. The chemical composition plays a final quiet role by fixing electron density for a given temperature and pressure. Lower heavy element abundance means fewer metal electrons, but at these temperatures hydrogen and helium provide an ample supply of free electrons, so the scattering opacity stays high and the continuum remains smooth. Where metals do matter is in setting the subtle balance of bound free edges and the strength of the iron bump. Both are weaker than in a metal-rich star, tilting the subphotospheric environment toward even more purely radiative behavior and simplifying the mapping from local temperature to emergent flux. Altogether, the subsurface layers form a thin, stable envelope that couples the deeper energy source to the photosphere through radiative diffusion moderated by a handful of opacity sources. Electron scattering dominates the opacity budget, free absorption, and a softened blanket of metal lines supply the absorption needed to thermalize, and a reduced iron opacity bump leaves only faint hints of shallow convection. Energy crosses these layers as a steady flow of photons that scatter many times, drift outward along the temperature gradient, and emerge at the surface with a spectrum that records the local conditions. The structure remains close to hydrostatic. The gradient remains just steep enough to carry the luminosity, and the system reacts on short radiative timescales to preserve balance as ionization and opacity adjust to the extreme temperature of a very early O-type photosphere. Farther beneath the subphotospheric layers, the stellar envelope carries energy outward almost entirely by radiation, and in a very hot, very luminous O-type star, this radiative transport sustains a smooth, persistent flow that links the deep power source to the thin photospheric skin without large overturning motions. The envelope is the region outside the convective core where hydrogen fusion no longer occurs. There, the temperature and density decline with radius, while pressure support shifts progressively from gas to radiation, and photons dominate both the bookkeeping of energy and the communication between neighbouring layers. Radiative diffusion describes the process photons scatter, or are absorbed and re-emitted many times, drifting from hotter to cooler zones along a gradient set by the opacity and by the need to carry the luminosity supplied from within, because hydrogen and helium remain highly ionized. Free electrons abound, and electron scattering stays a leading opacity over a wide span of depth, giving the radiation field a grey character that washes out sharp wavelength preferences and lets the energy flux respond primarily to the overall temperature gradient rather than to isolated spectral features. Even so, true absorption is essential to maintain local thermodynamic coupling, and free absorption, together with a softened forest of metal lines, provide the channels by which the photon gas exchanges heat with matter before scattering returns the photons to the stream. The envelope maintains hydrostatic balance at each radius, with gravity pulling inward and the sum of gas and radiation pressure pushing outward. In this star, the ratio of radiation pressure to total pressure grows large through the envelope, easing the density required to support the overlying weight and producing long, mean free paths in deeper regions than would be possible in cooler, denser stars. Where opacity rises with decreasing temperature as it does near the iron group, opacity bump, the radiative gradient must steepen to carry the same flux, and this local steepening can drive small convective pockets if it exceeds the threshold for buoyant instability. In the lower metallicity environment of the Large Magellanic Cloud, the iron bump remains present but weaker, so any convection that appears in association with it is shallower, thinner, and less efficient. It stirs on short vertical scales, seeds, microturbulence, and damps quickly into the surrounding radiative sea without building large cells or broad overturning flows. Beyond these localized pockets, the envelope stays radiative, with photons doing nearly all the work of moving heat outward. The efficiency of radiation in such conditions gives the envelope a built-in regulator. Should opacity rise modestly because an ionization edge strengthens with depth, or because density nudges a set of lines into greater importance, the gradient steepens, the local temperature drops slightly relative to the deeper layer below, and the increased contrast restores the required flux. If opacity falls, the gradient relaxes, and the flux remains matched to the luminosity set by the interior. The reaction timescale is short because photons cross many mean free paths. In a small fraction of the time it takes bulk material to move appreciably, so the envelope damps rapid perturbations and passes only gentle longer period variations outward. This damping helps explain why the visible light of very hot O-type stars is steady to within small limits even while the atmosphere and wind show fine time structure. The envelope smooths the delivery of energy so that the surface sees a near constant supply. In a frame that follows the slow outward decline of temperature and density, the energy flux stays nearly constant with radius when measured per unit area, because the luminosity is conserved and the spherical area grows only gradually across the envelope's thickness. The temperature gradient adjusts to this requirement through the Rossland mean opacity, which weights low opacities more heavily, because heat preferentially uses the easiest channels. With electron scattering, strong and heavy element opacity reduced by the galaxy's lower metallicity, the mean stays comparatively low, and the necessary gradient remains modest, a circumstance that further suppresses convection and favours radiative calm. Radiation pressure enters the structural equations explicitly through the Eddington factor, a ratio that compares outward radiative acceleration to inward gravity. In these envelopes, the factor approaches but does not exceed unity when averaged over depth, leaving a comfortable margin that holds the layers in place while still lightening their effective weight. Nearer the surface, where density is lowest and electron scattering sets the tone, the factor increases locally, but the envelope has already adjusted its gradient to avoid any runaway. In this regime, a phenomenon sometimes called envelope inflation, in more extreme cases would require a stronger opacity surge or a higher proximity to the radiative limit than is implied here. With reduced metallicity and a photospheric temperature near the hottest end of the normal sequence, the envelope stays compact, and any low-density extensions remain shallow compared to the stellar radius. The transport of energy coexists with the transport of momentum by waves launched at deeper boundaries. Gravity waves and acoustic waves can propagate through stably stratified radiative layers, but the strong radiative damping and the rapid diffusion of heat sap their amplitudes as they climb. Only small traces reach the photosphere, where they can modulate line profiles by minute amounts or contribute to narrow bands of low amplitude variability. The envelope also mediates the exchange of chemical information between the core and the surface. Rotationally induced circulation and shear can mix on timescales, long compared to a dynamical time, but short compared to the star's life on hydrogen-burning tracks. In a largely radiative envelope, such mixing is diffusive and slow, modulated by thermal stratification and by the same microphysics that set opacity. In a lower metallicity galaxy, initial abundances of nitrogen, carbon and oxygen start lower, so any surface enhancements inferred from spectra point more clearly to internal transport rather than to birth composition, and the efficiency of that transport depends on rotation and on the gentle stirring provided by thin convective pockets around opacity features. The link between energy transport and the stellar wind lies in the outermost envelope, where radiation pressure, electron scattering and line opacity act together to set the pressure scale height and the density at the base of the outflow. A smoother, steadier radiative envelope delivers a steadier boundary to the atmosphere, so the wind sees a stable supply of photons and density against which the line force can work. Small variations in the radiative gradient or in local ionization around the ion bump imprint only diluted signatures at the surface, consistent with the observed steadiness of the ultraviolet continuum against which wind lines form. Thermal timescales through most of the envelope are long compared to sound crossing times, but they remain short compared to nuclear timescales, so the structure is quasi-static in the present context, and evolves only gradually as the interior composition changes through fusion. That gradual evolution shifts the luminosity and the temperature profile centimeter by centimeter in a figurative sense, and the radiative transport adjusts continuously to keep carrying the changed flux, reinforcing the picture of an envelope that acts as a quiet conduit rather than as a source of dramatic fluctuations. Magnetic fields remain dynamically weak in these depths because gas and radiation pressures dominate. They follow the flow diffuse slowly compared to radiative processes and do not redirect the energy path. Altogether, the envelope of this very hot luminous O-type star functions as a radiative engine room. Photons stream outward through a medium where electron scattering and reduced heavy element opacity make for efficient diffusion. Thin ion bump zones introduce only mild localized stirring radiation. Pressure shares the load of hydrostatic support without unbinding the layers, and damping ensures that the surface receives an almost unwavering energy supply. In this configuration, the star maintains the high effective temperature of its photosphere and the large luminosity measured from its spectrum, while the envelope itself remains largely unseen. its presence inferred from the steadiness of the emergent light and from the subtle metallicity-dependent fingerprints it leaves on the path that energy follows from depth to surface. At the center, the core sustains hydrogen fusion under temperatures of many tens of millions of degrees Kelvin, and at densities high enough that matter behaves as a tightly coupled, fully ionized plasma, where particles move swiftly and collide often. In such conditions, hydrogen nuclei, which are protons, overcome their mutual electrical repulsion by quantum tunneling and bind to form helium through reaction chains that release energy as both gamma-ray photons and neutrinos. The dominant chain in a very hot, very massive star is the carbon-nitrogen-oxygen cycle, a catalytic sequence in which existing nuclei of carbon-nitrogen and oxygen capture protons, transmute through beta decays and return to carbon, while producing one helium nucleus and releasing energy. The cycle rate depends steeply on temperature, far more sharply than the rate for the proton-proton chain common in cooler stars. So the core's high temperature fixes the energy generation at a level that matches the observed luminosity without requiring a large fraction of the fuel to burn in any instant. The catalytic role of carbon, nitrogen, and oxygen means that at a lower heavy element abundance the cycle still operates, but with details that favor slightly higher central temperatures and densities to maintain the same energy output. The net effect is a core whose conditions reflect both mass and composition in a self-consistent balance with the surface luminosity. Radiation pressure contributes substantially to total pressure in the core, sharing the task of holding the star against its own gravity, with gas pressure from ions and electrons. The mix reduces the sensitivity of core pressure to temperature alone, and allows hydrostatic equilibrium to settle at values where the temperature gradient needed to move energy outward grows steep enough to trigger convection. A convective core is a region where buoyant motions carry heat more efficiently than radiation can, and in these stars the convective zone encompasses a large fraction of the central volume. Convection mixes hydrogen inward and helium outward, flattening composition gradients and keeping the nuclear burning region supplied with fresh fuel near its boundaries. This mixing also brings to the burning shell the catalytic nuclei that set the carbon-nitrogen-oxygen cycle pace, and it sweeps out local inhomogeneities so that on large scales temperature and composition vary smoothly with radius inside the core. The energy released in the cycle emerges first as kinetic energy of particles and as high-energy photons that share their energy quickly with the surrounding plasma. Photons scatter and are absorbed and re-emitted countless times as they diffuse outward, while neutrinos escape almost unhindered because they interact only weakly. This escape removes a small but measurable fraction of the energy budget and provides a silent sink that depends on core temperature and density. The balance among energy production, radiation, and convection sets the temperature profile. Deep inside, where burning is most intense, the gradient is set by the convective rules that keep layers marginally stable against buoyant overturn, and farther out where the nuclear rate falls and opacity remains high, radiation takes over and the gradient shifts smoothly toward the radiative value. The composition profile changes with time as hydrogen is consumed and helium accumulates, but at any given moment the central concentration of helium rises, while hydrogen remains plentiful enough in the mixed region to keep the cycle active at the required rate. The microphysics of the cycle involves a chain of reactions whose slowest step throttles the overall pace. At the high core temperature of this star, the slow step is still slow enough to control the chain, but faster than in cooler stars by a large factor, which is why the energy generation rate responds so strongly to even small changes in temperature. The dependence acts as a regulator. If the core were to heat slightly, the cycle would speed up markedly. raising the energy flux, increasing radiation pressure, and expanding the core just enough to cool back toward balance. If the core were to cool slightly, the reverse would occur. This thermal self-regulation paired with hydrostatic equilibrium maintains a steady burning rate compatible with the luminosity measured from the spectrum. Electron degeneracy does not set the pressure here. Temperatures remain high enough and densities low enough that pressure is dominated by classical gas and radiation terms, and the core behaves as a hot plasma rather than as a degenerate object. The equation of state is therefore simple in its leading terms, which helps stabilize the convective profile and keeps the mixing smooth. The efficiency of convective transport depends on opacity and on the temperature gradient needed to carry the flux. With electron scattering important, and with lower heavy element opacity than in a metal-rich star, the radiative conductivity is relatively high, so the gradient needed to pass the flux is modest, except at the very center where generation is greatest. Even so, the enormous luminosity flowing through a small central volume makes convection the preferred carrier there, and it remains so across a large inner region. Nuclear statistical equilibrium does not apply. Temperatures are far below the values where nuclei would equilibrate through rapid captures and photodisintegration. Instead, the carbon-nitrogen-oxygen cycle and ancillary side chains govern composition changes with the slow beta decays, fixing the timing between captures. The sequence converts 4 protons into 1 helium nucleus per cycle, releasing energy that later appears at the photosphere as the blue-white continuum and as the ultraviolet flux that gives the spectrum its hot character. The rate of helium buildup determines the mean molecular weight of the core plasma, and as helium accumulates, pressure support requires a small increase in temperature to maintain balance, which in turn sharpens the nuclear rate and keeps the energy supply aligned with the outward demand. The convective boundary is not a perfectly sharp interface. Mixing can overshoot slightly beyond the formally convective region as rising elements penetrate into the surrounding stable layers before losing buoyancy. This overshoot extends the fuel supply marginally and softens gradients in composition near the edge of the core effects that detailed models include within measured uncertainties. Rotation adds a further gentle mixing through large-scale circulation that carries material along meridional paths, but in a strongly convective core. This additional transport is a second-order contributor compared to buoyant overturn. Magnetic fields can be amplified by shear and by convective dynamos in the core, yet their pressure remains small compared to gas and radiation pressure, and their primary role is to ride with the flow while possibly influencing angular momentum distribution on long time scales. The neutrinos produced in beta decays and by secondary processes leave the core without depositing energy, carrying away a fraction of the power. Their role in the present balance is modest, relative to the photon luminosity, but they are a precise part of the bookkeeping of nuclear energy release and slightly reduce the thermal energy that must be transported by radiation and convection. Opacity in the core arises from electron scattering free processes, and at these temperatures and densities from electron-ion interactions that remain well described by classical forms. Line opacity plays little part because atoms are fully ionized. The mean free path for photons stays extremely short, and the radiative timescale across the core, though far longer than the dynamical timescale, remains shorter than evolutionary timescales, so energy adjusts smoothly to changes in nuclear rate. Observationally, the core cannot be seen directly. Its state is inferred from the surface luminosity, the effective temperature, and the spectrum combined with models that anchor the mass and composition to match the measured classification. Those models consistently place very hot luminous O-type stars on hydrogen-burning tracks, with large convective cores and radiative envelopes producing ultraviolet-dominated spectra and fast winds that align with the conditions described in the outer layers. In this inner region, the present configuration is one of steady hydrogen fusion through a temperature-sensitive catalytic cycle, vigorous convective mixing that maintains a broad fuel reservoir, a pressure balance shared between radiation and gas, and a quiet radiative handoff to the surrounding envelope. The central engine thereby supplies the outward energy that the photosphere re-emits, the wind translates into motion, and the surrounding cavity receives as heat and ionization, all held together by the microphysics of nuclear reactions and the macroscopic constraints of equilibrium in a hot massive stellar core. Chemical information rises from deep layers to the surface through a combination of convective supply within the core, slow mixing in the radiative envelope, and mass loss that peels away the outermost skin, and together these processes leave subtle fingerprints in the spectrum that observers use to infer the internal story. In very hot, very luminous O-type stars, the convective core occupies a large central volume and keeps the catalytic nuclei of the carbon-nitrogen-oxygen cycle well stirred within its boundaries, while the surrounding envelope remains largely radiative and resists vigorous overturn. Even so, several channels carry traces of nuclear processing toward the photosphere. Rotationally driven circulation moves material along broad meridional loops that connect equatorial and polar latitudes at different depths. Shear instabilities where rotation speed changes with radius can shred small gradients and diffuse composition outward. And thin convective pockets associated with the iron opacity bump just below the surface add microturbulent stirring that helps blend layers on short vertical scales. The net transport is modest compared to the rapid mixing of the core, but over the timescale of hydrogen burning, it is sufficient to alter the outermost composition by small measurable amounts. The lower heavy element abundance in the Large Magellanic Cloud sharpens this sensitivity. Initial nitrogen, carbon and oxygen start at lower values than in the Milky Way, so any enhancement of nitrogen or depletion of carbon and oxygen at the surface stands out more clearly against the baseline. In practice, high-resolution spectra of very early O-type stars reveal line ratios among high ionization stages of nitrogen and oxygen that differ from pristine expectations and model atmospheres that include the appropriate temperature, gravity and metallicity. Reproduce these ratios only when a small degree of internal mixing is allowed. The pattern favored by the carbon-nitrogen-oxygen cycle is simple nitrogen rises as carbon and oxygen share protons in the catalytic loop, so surface material that has been lightly processed shows a mild nitrogen enhancement and a corresponding softening of carbon and oxygen lines at fixed temperature. The strength of this signature depends on the extent of mixing and on the cumulative effect of mass loss. The wind removes outer layers continuously, and as those layers thin, slightly deeper material reaches the photosphere. In a lower metallicity environment, the mass loss rate is reduced because fewer metal lines absorb radiation to drive the wind, so this peeling proceeds more slowly than in metal-rich stars, but the long timescale of the hydrogen burning phase ensures that the effect is not negligible. The combination of slow envelope mixing and slow abrasion by the wind yields a photosphere that late in hydrogen burning can carry a modest imprint of core-side chemistry without exposing fully processed layers. The diagnostic power of these surface clues relies on careful separation from temperature effects. At the effective temperature near 52,500 degrees, Kelvin helium lines set the classification and determine the basic ionization framework, while nitrogen and oxygen lines add secondary information that depends on both temperature and abundance. Synthetic spectra computed for the measured gravity, microturbulence, and metallicity, when adjusted for small abundance shifts, match observed line depths in ways that point to nitrogen being fractionally enhanced relative to the initial Large Magellanic Cloud ratio, and to carbon and oxygen being slightly depressed. The changes are not large enough to approach the patterns seen in classical Wolf-Rayet spectra, where the wind and the atmosphere merge and fully processed layers dominate. And this difference anchors the description of the present star as a normal, though extreme O-type, with emission features rather than as a star whose surface is a direct window into the core. Rotational speed modulates the rate of mixing. Higher rotation amplifies meridional circulation and shear, while lower rotation damps them, and the projected rotational broadening measured from helium and high ionization metal lines provides a boundary on plausible internal rates. In cases where line widths indicate moderate rotation, models find that the observed abundance shifts can arise during hydrogen burning without invoking extreme transport. The envelope's radiative stability limits mixing to gentle cumulative diffusion. Gravity darkening may introduce weak latitudinal differences in surface temperature and brightness, but those differences are too small to produce false abundance patterns at the level under discussion when averaged over the visible hemisphere. Polarization and line profile symmetry suggest that large, highly asymmetric chemical spots are absent, consistent with a global mixed photosphere rather than with localized patches of altered composition. The wind itself modifies the appearance of abundance diagnostics through clumping and porosity. Clumps raise local density, increase recombination rates, and can strengthen certain emission features relative to smooth models. Porosity lowers effective opacity along some paths and can reduce the depth of resonance absorptions. When models include clumping factors consistent with the ultraviolet windline shapes, the inferred abundance shifts remain, indicating that they are not artifacts of wind structure, but are rooted in the underlying photospheric composition. In the near ultraviolet resonance lines of carbon, nitrogen, and oxygen form in the accelerating outflow and respond to both abundance and ionization. By combining these with photospheric lines at longer wavelengths that form deeper and that feel the wind less, analysts separate abundance from kinematics and fix a consistent picture in which nitrogen is mildly elevated. The metallicity context matters again when linking these surface clues to interior processes. With lower initial metals, the mass fraction of catalytic nuclei available to start the carbon-nitrogen-oxygen cycle is smaller, and the core responds by operating at slightly higher temperature to meet the same luminosity, which in turn enhances the cycle's sensitivity to temperature. This steeper sensitivity means that modest internal temperature differences can produce significant local processing, but the convective core's mixing erases those local variations, leaving a uniform processed composition in the burning region. The envelope then acts as a filter, allowing only a faint echo of that processed material to reach the photosphere through slow diffusion and through the gradual loss of the outer skin. The echo carries more contrast against the low metallicity baseline than it would in a metal-rich environment, which is why stars in this galaxy can display clearer evidence of light processing at the surface, while still residing on hydrogen-burning tracks. The observational consequences extend to the helium fraction as well. Slight helium enrichment at the surface is compatible with the same mixing picture that raises nitrogen. Helium lines primarily trace temperature and gravity at these high temperatures, but detailed fitting allows small abundance shifts that improve the match to line wings and cores, again within margins, consistent with gentle transport rather than with exposure of deep, fully processed layers. Together, these adjustments remain within the range that keeps the photosphere firmly in the regime of a normal O-type atmosphere rather than a wind-dominated pseudo-photosphere. The presence of emission features in some helium and metal lines does not erase these clues. It overlays them with kinematic signatures that models can account for. A multi-wavelength fitting across ultraviolet and optical bands recovers a consistent set of abundances when wind effects are included. This coherence between independent diagnostics strengthens the inference that interior mixing and slow mass loss have nudged the photospheric chemistry away from its birth composition. The star's environment also shapes what can be read. Reduced dust and strong ultraviolet transparency in the Large Magellanic Cloud improve line-of-sight clarity and lessen uncertain reddening corrections, so the intrinsic spectrum is recovered with smaller systematic error than might be faced along dusty Milky Way paths. The remaining uncertainties arise from microturbulence clumping and the choice of atomic data, all of which are folded into the error bars of derived abundances. Within those uncertainties, the same picture holds a surface showing mild nitrogen enhancement, slight carbon and oxygen depletion possible, small helium enrichment, and no large anomalies beyond those expected from standard evolutionary paths for very massive stars at low metallicity. Such a surface composition aligns with the star's place among the hottest measured photospheres of normal stars because it indicates the interior remains on hydrogen burning and has not yet advanced to stages where deeper products dominate the atmosphere. The spectrum therefore carries messages in the mix that, when interpreted with models tuned to the temperature, gravity, metallicity, and wind structure, reveal how core processes envelope transport and mass loss. Together write faint but definite chemical notes into the light that escapes from the photosphere today. Mass loss steadily alters the star by removing material and angular momentum through its fast radiation-driven wind, and the pace of that change depends on luminosity, metallicity rotation, and the clumped structure of the outflow. A line-driven wind hands momentum from photons to ions in many metal lines, so the rate at which mass leaves the surface scales with the number and strength of those lines and with the total photon flux. In a lower metallicity environment, fewer lines soften the coupling and reduce the mass loss rate compared to an otherwise similar star in a richer environment, while the large luminosity keeps terminal speeds high. Clumping raises the local density inside pockets and makes emission diagnostics overestimate the mass flux if models ignore structure. So the true rate is lower than smooth wind fits might suggest a correction that matters for long-term evolution, because the integrated mass removed over a hydrogen-burning lifetime sets later structure. Angular momentum leaves with the wind because material carries spin as it departs. The loss slows the surface over time and can reduce rotational mixing in the envelope, feeding back on how surface abundances change. The strength of this braking depends on the lever arm set by any magnetic torque and on the latitude pattern of mass flux. With no strong magnetic confinement, the pattern remains nearly spherical, and the torque follows the mass rate. The Eddington factor, a ratio of radiative to gravitational acceleration, approaches high values in very luminous stars and sets the margin by which radiative support lightens the envelope. When that margin grows, the outer layers become more susceptible to changes in opacity, yet in a lower metallicity case, the ion opacity bump is weaker, and the envelope stays compact, so steady winds dominate mass removal rather than large-scale inflation. Over time, these winds thin the outer layers and bring slightly deeper, mildly processed material to the photosphere, continuing the gentle trend identified in the surface chemistry. The wind momentum, the product of mass loss rate and terminal speed, tracks luminosity in a way used as a diagnostic, and at the measured temperature, and luminosity it aligns with the fast lean outflows typical of very early O-type stars in the Large Magellanic Cloud. Feedback into the surroundings continues as the wind inflates and maintains the ionized cavity, piles gas into shells and seeds, the medium with energy and momentum. Inside the star, the core burns hydrogen through the carbon-nitrogen-oxygen cycle, while the envelope transports energy by radiation. As hydrogen is converted to helium, the mean molecular weight in the core rises, and small adjustments in temperature and density keep equilibrium and maintain the luminosity delivered to the surface. The gradual change in core composition sets the stage for future structural adjustments without imposing abrupt surface signals during the present phase. Evolutionary pathways for very massive, very hot stars include several branches that depend on mass rotation and metallicity. In one pathway, slow winds at low metallicity let the star retain more mass during hydrogen burning, keeping a large convective core and a compact envelope until hydrogen is depleted in the center, after which the structure readjusts as helium burning begins and the surface temperature and wind properties shift. In another pathway, if rotational mixing is efficient composition, gradients stay shallow and the star can evolve almost homogeneously, keeping a hot surface and moving in temperature and luminosity without developing a deep composition contrast between core and envelope. The degree to which this occurs depends on initial rotation and on the braking effect of the wind, which weakens mixing as spin falls. In a pathway seen in some very luminous objects, envelopes near the radiative limit can experience episodes of enhanced mass loss, driven by continuum opacity, with outflows stronger than steady line-driven winds on short intervals. Whether such episodes occur depends on proximity to the radiative limit and on opacity structure in the outer layers, both of which are tempered by reduced metallicity in this galaxy. A later pathway enters when surface layers become helium-rich, and mass loss, even if modest at any instant, has peeled enough material that the star presents a hotter, more stripped spectrum. At that stage, spectral types associated with strong emission can appear as the wind and atmosphere merge into an optically thick outflow. The present state does not fix which of these branches will be followed, yet it constrains the tendencies. Lower heavy element content favors smaller steady mass loss. During hydrogen burning, rotation loses angular momentum through the wind and moderates its own mixing over time, and the compact envelope argues against large inflation, while hydrogen burning continues. Binarity can in principle redirect evolution through mass exchange or tidal spin-up, but without direct evidence for a companion, the single star picture frames expectations, with a note that undetected binarity remains a general caveat in studies of massive stars. As mass leaves the surface, gravity slowly decreases for a fixed radius, but radius and luminosity can both adjust through interior changes, so the surface temperature does not follow a simple, monotonic trend during hydrogen burning. Models tuned to this metallicity and luminosity show small drifts that keep the photosphere in the very hot regime, while hydrogen remains abundant in the core. The wind composition will continue to evolve, along with the photosphere carrying slightly more helium and nitrogen, and slightly less carbon and oxygen as mixing and peeling proceed, and the ultraviolet resonance lines will reflect these changes through gradual shifts in depth and profile, provided the wind structure and ionization remain comparable. Momentum and energy deposited by the wind will keep shaping the local bubble and shell, with the hot shocked layer persisting, because reduced metallicity weakens cooling. The integral of this mechanical feedback across time records the star's cumulative influence on its surroundings and helps set conditions for later star formation in the neighborhood by clearing, compressing, or stirring the gas. From the perspective of the star's internal bookkeeping, the controlling quantity during this phase remains the central hydrogen fraction, which falls steadily, while the luminosity and effective temperature stay within the range that defines the present classification. When the fraction drops below a threshold, the core contracts, the envelope responds, and new burning stages begin. The exact surface path through temperature and wind properties at that transition depends on the remaining mass, the spin rate, and the metallicity-dependent opacity. In all cases, the physics already in place continues to act. Radiation drives the wind through the available lines. Clumping modulates observed diagnostics, rotation, influences mixing and line widths, and the lower heavy element content sets a leaner interaction between light and matter than in metal-rich stars. The star's present configuration with a very hot photosphere, a powerful but relatively low mass flux wind and mild surface abundance adjustments, is consistent with a hydrogen-burning object that sheds mass at a pace shaped by reduced metallicity, and that carries forward multiple plausible evolutionary routes under the same physical rules already observed in its atmosphere and envelope today. Knowledge about a star at the hot edge of the normal sequence rests on measurements filtered through models, and each link in that chain carries limits that define what can be claimed with care. Effective temperature comes first because it anchors luminosity, ionization, and classification. It is inferred by matching observed spectra and broad band fluxes to model atmospheres that include electron scattering, reduced line blanketing, appropriate to the Large Magellanic Cloud, and non-equilibrium level populations. The match depends on the extinction law along the line of sight on the total dust column and on the distance used to convert flux to luminosity. The Large Magellanic Cloud distance is well constrained, yet small differences in adopted values propagate into luminosity and into the bolometric correction that translates the observed blue-white continuum into total output. The extinction law varies across environments, and a curve with slightly different ultraviolet shape changes the recovered far ultraviolet flux more than the optical shifting the best fit temperature by small amounts. Metallicity enters twice through the true abundance pattern in the photosphere and through the line list used to compute opacity. A thinner line forest lets ultraviolet photons escape more easily, but the exact degree depends on atomic data that are still updated as measurements and calculations improve. Non-equilibrium radiative transfer controls line formation in these hot dilute layers, and different modeling codes adopt different treatments of microturbulence, line broadening and geometry, leading to systematic offsets in the temperature scale for the earliest O-types that are small but not zero. Gravity follows from the wings of helium and hydrogen lines shaped by stark broadening in an electron-rich gas. Those wings must be disentangled from wind emission that can fill cores and from rotation that broadens profiles. The projected rotational speed is measured from line widths, but the inclination is unknown, so a family of solutions in rotation and gravity can fit the same data. Polarization offers constraints on shape, yet the expected signal in an almost spherical electron scattering atmosphere is minute, and current measurements yield upper limits more often than secure detections, leaving a range of allowable asphericities. The wind mass loss rate and terminal speed are read from resonance lines in the far ultraviolet and from recombination features at longer wavelengths. Clumping and porosity blur the map between line depth and true mass flux. Denser pockets strengthen emission and can mimic a larger global rate if ignored. Porous channels lower effective opacity and can hide material. Fits that include clumping recover lower mass loss rates than smooth models, but the clumping factor itself is an inference that changes with adopted clump size geometry and ionization, and different assumptions move the derived rates within a band of plausible values. Terminal speed is tied to the blue edge of absorption troughs, yet that edge depends on signal to noise and on how completely the line saturates at the highest velocities, so quoted values include uncertainties that reflect both physics and data quality. The presence or absence of weak magnetic fields remains another quiet limit. Fields at modest strengths can guide near-surface flows and imprint periodic changes in line polarization, but in hot luminous stars with fast, nearly radial winds, the level required to confine the outflow is high, and non-detections at current sensitivity leave open a wide parameter space where fields exist but do not dominate. Binarity is a separate axis of uncertainty. A faint companion can alter line profiles through blended features, add light that changes the inferred temperature and gravity, or stir winds where streams collide. Radial velocity monitoring in crowded associations faces confusion from wind variability and from limited time coverage, so a widely spaced or low-mass companion can elude detection. Claims about singular evolution therefore carry the caveat that a hidden companion cannot be ruled out purely from a single epoch spectrum. Photometric steadiness in the visible supports a compact radiative envelope feeding a stable photosphere, yet the amplitude limits depend on cadence precision and the subtraction of association light that can veil weak signals. Interstellar contamination in the ultraviolet by narrow lines of intervening gas can blend with stellar features and bias wind fits, if not corrected with care. Atomic data for high ionization stages important at these temperatures continue to improve, and revisions to oscillator strengths or collision rates alter synthetic spectra at the percent level in key lines, which in turn adjust best fit abundances and microturbulence. Even the definition of temperature used for comparison requires discipline. Effective temperature refers to the photosphere and to the total energy per area. Shock temperatures in the thin wind or characteristic temperatures in optically thick Wolf-Rayet layers are different physical quantities. When this star is described as among the hottest measured photospheres, the comparison is to other non-degenerate photospheres at optical depth of order unity, not to plasma spikes in shocks and not to winds where the photosphere sits deeper. This distinction answers labels that hinge on hottest by grounding them in how temperature is defined and measured. Luminosity measured in concert with temperature draws on the same distance and extinction inputs, and on bolometric corrections that depend on metallicity. Small shifts in any step move the placement of the star on a diagram of luminosity against effective temperature by small but finite amounts, and evolutionary tracks drawn for slightly different heavy element mixtures thread that diagram along paths that are close together near the hot luminous corner. Matching a point to a track within that thicket gives mass and age estimates with error bars that reflect both measurement and model sets. The interior mixing rate that surface abundances imply is likewise model dependent. Inferences of mild nitrogen enhancement and modest helium enrichment rest on synthetic spectra at the measured temperature and gravity. Wind clumping corrections and microturbulent velocities change the detailed fit and shift abundances within stated uncertainties. The envelope ion opacity bump sets whether thin convection pockets exist. The bump's strength at this metallicity is measured indirectly through its effects not directly, and different opacity compilations yield slightly different bump heights, moving the boundary between purely radiative and weakly convective by a narrow margin. Kinematic structure in wind lines records embedded shocks and clumps. The migration speed of notches across absorption troughs is a tracer of acceleration and flow time, yet it relies on high cadence coverage that is often sparse. Soft high-energy emission from thin shocked wind layers supports the shock picture, but interstellar absorption toward the Large Magellanic Cloud attenuates the signal, and the partition between intrinsic emission and absorption along the way adds another modelled step. Across all of these pieces runs a common thread: the star's identity as a very hot, very luminous O-type object in a lower metallicity galaxy is robust. The photospheric effective temperature sits among the highest measured for normal stars, and the wind is fast and lean, yet each quoted number carries an uncertainty shaped by extinction, metallicity, non-equilibrium transfer, clumping rotation, and the finite sensitivity of instruments. These limits mark what remains to refine rather than overturn. Better constraints on the ultraviolet extinction curve along the exact line of sight, tighter atomic data for high ionization lines, longer time series in the ultraviolet to track migrating wind features, deeper searches for subtle polarization, and improved treatments of clumping geometry in radiative transfer will narrow the bands. Until then, caution maintains the language used here among the hottest measured photospheres, not the hottest object. Fast powerful wind at reduced mass loss, early O-type with emission features consistent with a stratified atmosphere above a thin photosphere, and a structure that aligns with hydrogen burning in a convective core feeding a radiative envelope. Within these present limits, the picture remains coherent and complete for the current state, bounded by measurements that are precise enough to place the star securely, while honest about the small ranges that define its exact numbers.